All right, section 19.8. So we've looked at oxygen nucleophiles. We talked about how to make an acetal in section 19.5. In section 19.7, we looked at how to blow it apart, right, just by treating it with dilute acid. In section 19.7, we talked about nitrogen nucleophiles. We talked about how to make an imine and an enamine. And then again in section 19.7, we addressed how to hydrolyze an imine and an enamine. And now in section 19.8, we're going from uh, oxygen to nitrogen to sulfur. So now we're talking about sulfur nucleophiles, and you should know what a thiol is, right? So you know that a thiol is just the sulfur analog of an alcohol, just a lot stinkier, right? They smell very bad. So a ketone or an aldehyde, good news, if you understood what happened in, or what was happening in section 19.5 with an alcohol, the great news for you is that thiols react in pretty much the exact same way with the ketone or aldehyde. So if we have two equivalents of a thiol and a ketone, a catalytic amount of acid, of course we remove water. That's what they're showing over here. You form instead of an acetal, right? Everybody here by now knows what an acetal is. That's when we have oxygens. Okay, again, this is an acetal. So this, if you replace the two oxygens with sulfur, you get a thioacetal. So a thioacetal. Now, you remembered that one of the alcohols that we used was a diol. We used ethylene glycol like this. So if you replace that, so we get 1,2-ethane thiol, which is this compound here. In that case, you can make a cyclic thioacetal. And we looked at cyclic acetals as well. The thing about the cyclic acetal that, the cyclic thioacetal is when I was in graduate school, I did a reaction or some investigations on cyclic thioacetals. And I went to my first job interview out of graduate school. And the first question that I was asked had to do with the cyclic thioacetal. I never forgot it because I couldn't answer it 100%. I was only halfway sure of my answer. That the guy asked me, and I'm talking about a guy with 30 years experience doing chemistry, and I had what, a couple of years. And I said, I'm not 100% sure, but I think, this is what would happen with this cyclic thioacetal. And the guy said, after he waited for me to sweat it out, he goes, I'm not sure either. I'm really not sure either. Anyhow, it was kind of funny. All right, so you remember how we saw how to reduce or to how to reduce a hydrazone or an imine using the Wolff-Kishner reduction? Well, you can also reduce a thioacetal by treating it with something called Raney nickel. Now, our book goes into a little bit of detail about Raney nickel, how it's an alloy between nickel and aluminum, and it has a porous surface. Sometimes people call it spongy nickel. I'm not kidding. It's like SpongeBob nickel, right? Anyhow, it's like spongy nickel. And again, it's because it's porous and it can absorb or adsorb hydrogen onto it, which is required for the reduction. And another thing about Raney nickel that I never forget is that it's pyrophoric. It ignites spontaneously in air, so you have to be really careful when you're working with it. But if you think about it, we could start with a carbonyl, right? We could start with a ketone. Okay, we could treat this with the 1,2-ethane dithiol, a catalytic amount of acid, okay, and of course the removal of water, and we would make a thioacetal, and then we could reduce that with Raney nickel to an alkane, right? And that's what's shown here, right? It's showing the whole dang thing. Well, hold on, that gives us yet another method for doing this, because now we have the Raney nickel reduction, but we also have the Clementine reduction. So I'll write them over here, Clementine reduction, and we also have the Wolff-Kishner, okay? Wolff is German and Kishner is Russian, I'm pretty sure. But anyhow, so we also have those two methods, right? A Clementine can reduce a carbonyl, as can a Wolff-Kishner. And this is something that's going to come up again more and more in organic chemistry too, is that we learn more than one way to do, a particular transformation. Why? Because a good organic chemist, she or he will always have, a couple of ways or a couple of ideas as to how to affect any transformation in the lab. Well, with those two slides in mind, so literally two slides, the formation of the thioacetal and then the reduction of the thioacetal using Raney nickel, let's take a look at a question. It just says predict the major product for each of the following reactions. I'm going to do one better. I want to write down the intermediates. Right, if we take this ketone and we treat it with a catalytic amount of acid, 1,2-ethane dithiol, That's the name of that compound. We would end up with what? We would end up with a cyclic thioacetal. I'm going to write it down just because I want to be thorough with my students. So we have the 2 sulfurs and we have the 2 carbons in the bridge. Then upon treatment with rainy nickel, that just goes away. And our book actually addresses the mechanism by saying not much more than the mechanism of rainy nickel reduction is beyond the scope of this book. Okay, I think it's pretty complex. And so it's something that's not even covered in this textbook whatsoever. So there's no mechanism to know there. All right, what if we had an aldehyde? Here we have an aldehyde. We treat it with acid, our dithiol. What are we going to make? We're going to make our cyclic thioacetal. So let's draw that out. Make sure to indicate that proton. And you've got your cyclic thioacetal. Then when you blow that apart with rainy nickel, so I'll use my red pen again. You blow that apart with rainy nickel, okay? And you're going to end up with what? You're going to end up with this. Oops. Come on. There you go. 2-methylbutane. I can't think of any circumstances under which I would want to take an aldehyde and just make 2-methylbutane, which would probably just go up the smokestack, right? It's probably so volatile. But anyhow, it's still a good exercise. And so, you know, what's the bottom line of the whole section on sulfur nucleophiles? In my opinion, it's nothing more than you got a new way to reduce a carbonyl, and that's it, my friend. Okay, you've got a brand new way to reduce a carbonyl. There you go. So sulfur nucleophiles. Well, I want to talk to you about one more section before we take a break, and that's the section on hydrogen nucleophiles. And the reason why is because it says here, recall. That's a politically correct way of saying we've covered this already. We covered this way back in Organic Chemistry 1. I just want to refresh your memory. We covered this in Organic Chemistry 2, but more towards the beginning of the class in the section on alcohols, which would have been what, chapter 12. Sorry, got too many thoughts in my mind. But anyhow, hopefully you remember that if you take an aldehyde or a ketone, you can reduce it to an alcohol. An aldehyde, you can reduce it to a primary alcohol. A ketone, you can reduce to a secondary alcohol. And how would you do that? You can use either lithium aluminum hydride, which is a 2-step process. Second step is water. Or you can just use sodium borohydrate with a polar product solvent like methanol, ethanol, or water. Now, notice that these reductions are carried out under basic conditions, okay? Because hydrides are strong nucleophiles. If you had an acid present, it would destroy the hydride. Just to refresh your memory on the mechanism, and again, our book goes into a little detail saying, you know, the mechanism of this reaction of these hydrogen or hydride reductions, I should say, are a little more complex than the treatment that is shown here, but this is going to suffice for our class. First step is a nucleophilic attack. Here they're showing reduction with aluminum hydride, lithium aluminum hydride, and then we make an oxide, which gets transferred by a proton in the second step, right? So this is the first step, treatment with LAH, and then in the second step, what do? You treat it with water, right? You throw water on it. Well, I want you to think about the stereochemical considerations that have to be taken into account, right? Because a ketone, the carbonyl carbon is sp2 hybridized. It is trigonal planar. It's flat as a pancake. And so that hydride, and I'm going to just write a hydride atom, which isn't technically correct, but the hydride can attack from the front face of the molecule, or it could attack from the back face of the molecule. All right, so since it can attack from either face of the molecule, when we end up with a new stereogenic center, we actually end up with a racemic mixture. So that's something that you want to keep in mind whenever you treat a ketone with a hydrogen nucleophile.